Swayam Prabha, free DTH channel for education.
So today let us start about the Fourier series. Okay, so in this case we are going to see. Okay, fine. Yeah. Okay. So so far we have seen the first order ODE and second order ODE, and today we are going to talk about some more thing called Fourier series. This is going to give a idea for solving the PDE. Means we are going to move from ODE to PDE. So for whenever we are going to solve the PDE problem, what we are going to get is that we are going to get some kind of series solution is going to come. Already we have seen some series solutions in the ODE, like power series solution we have seen. Now we are having another Bessel series. Okay, so that is like a Fourier series which has many applications that we are going to see, and there is a Fourier integral also that also we will see. Okay, so how it is going to come and helpful for us. Okay, and this is going to be a baseline or basic things for our PDE problems also. So I just give a brief history about that. Many of the engineering problems or many of the today's advanced world, whatever we have the technology, many of the things were developed during the world wars. Okay, during the wars they had the urgency to develop some of the things, and that due to that they have developed. For example, optimization theory. If you see, many of the things they have developed using during the world war. Similarly. If you see this Fourier series problem, so the Fourier was part of, I think, just check it, I think Napoleon's military, okay, where he was contributing to the uh, people in the warfare, okay. So in the warfare, what they got was, they got a problem of the cannons. The cannons means the tank, okay, the military tank which they are trying to attack on the opponent country or some enemy country. So they the problem was that was getting more cool, more heat, okay, because it is pushing that bomb or the material out of that cannon, and then it is giving more heat to that. What they want is they want to develop something like that should be cooled as soon as possible. Okay, so that they can launch the other one, and then that they can put that bomb on that. Means the cannon can send more bombs to the enemy's quarters. So for this, what he developed was he developed some theory, and from that he derived something called heat equation. Okay, if you see the heat equations history, you can see that. Okay, some of the textbook maybe this history may be there. So during that warfare time only he developed. Similarly, like calculus theory and other things, he was developing during the time of the pandemic situations uh, in London by Newton. Something similar to that. Okay, in Fourier also developed during that warfare time. So this was developed the heat equation and this Fourier series. So these are all the things which was developed during that period. And he developed something different. Okay, and then later on it was made many more changes. Finally, this paper got accepted, etc. Okay, so this is the basic history behind that. Now, what we are going to do is that we are going to see some of the Fourier series and how it is going to helpful for engineering problems, etc. So this has plenty of applications in engineering. Okay, that also probably like electrical engineering and mechanical engineering and even geotechnical engineering. So many of the places this Fourier series or Fourier transformation is going to be useful. Okay, so the basic idea behind that is this Fourier series only, and for that basic idea, we are going to go back to our school days physics or school days mathematics, and then we are going to see. Okay, so let's see that. So let's give we have seen power series already. Okay, the power series is given like this. We have seen that power series something like summation a n into x minus x naught power m we have seen. Okay, so this is the power series we got am into, okay, x minus x naught power m we got. Now we are going to check other another series called a trigonometry, okay, which is involving trigonometry function like sin x, cos x, okay, mostly the sin x, cos x function we are going to deal with, and then we are going to see. So this is power series. Whereas in Fourier series, what we have is that we are going to represent, okay, Fourier series represent the periodic functions in terms of cosines and sines. Okay, so this is the basic idea, but we will extend that idea to not only periodic function, non-periodic function also will extend. Okay, so these are the infinite series that represent periodic functions in terms of cosines and cosines. So first line is it's a series. So series already we know. So already we have seen. So sequence we know. Suppose I have a1, a2, etc., an, etc. Okay, these are all real numbers or complex numbers we can take. Okay, a1, a2, an are real numbers. Then we say this is a sequence. Okay, so means we can arrange that in a order. So the basic definition is that if x is any set, okay, the sequence is definition is as follows. Okay, you map f is x from x to r, okay, such that you can write that you can assign some values such that, okay, so for each n, okay, so not in general you can write that, but for this sequence what we are going to take is we are going to take f is a mapping from n to r, okay, means what I am going to do is that I am going to assign for each n, I am going to assign a value from the set, okay, so some x is given. For that what I am going to do, I am going to assign a value for that. So a1, a2, an I am going to assign. So suppose I take one value here, okay, I take there are plenty of elements that are in x, okay, x is a non-empty set, there are plenty of elements I can take it. Even if it's not a single element, so I can take it, okay, so plenty of elements I can take. For each n, okay, I am going to assign. So suppose I found the element x, okay, x in x, okay, then I can assign f of 1 equal to x, I can assign f of 2 equal to, again I will take another element, okay, so this is, since I take corresponding to 1, I call this x1. Similarly, if I take f of 2, I am going to assign x2. So that means I am going to assign for each natural number, I am going to assign a value, x1, x2, etc. Okay, so this one I am going to assign that. So this x I am going to take it as r, okay. So if I take that, or even you can generalize that, like you don't need to take it r, you can just say like suppose it is belong to x, you can find a mapping g from x to r, okay, g from x to r in such a way that this is a mapping. Therefore, what I can do is that I can do some other mapping here. I can take a composition. So g of x1 also I can take. So this is nothing but a general sequence representation. So let's forget about that. The sequence representation is nothing but you are taking some elements and then arranging in some order. Okay, for engineering students, maybe that is sufficient. So then what we have is we check whether it is or not converging. Okay, whether it is converging or not converging, etc. DC. So then further we check whether a series means a1, a2, an are there. So I check whether that is going to that is I arranged it. Since these are all real numbers, okay, these are all real numbers. I am going to check if I sum it up, what is going to come. Okay, whether that is also going to give some result, finite result or not result. So those things we are going to see. Okay, so that is the series one. Now we have seen the power series. Similarly, we are going to see the Fourier series. Now for periodic function, what we are going to see is that for periodic function, so we need to, second term is periodic, the key term that is periodic function. So infinite series, I have defined already. This is an infinite series, because the power series already in the last class. So now second term is periodic function. What is the meaning of periodic function? So that we have to see. This you might have already seen in your school days or some of the integral courses. So periodic function means f is any function. Okay, f is any function. We call this f is periodic if what you can find is that f of x is defined, okay, f of x is defined for all x, okay. So suppose f is defined from some x to some r, okay, or x to some y also I can take, okay, not only x to r, you can take any x to y. So f of x is given, okay, f of x is some x to y it is given. Now what you have to do is that whether it is periodic or not, you have to see, okay. So you assume that this x is equipped with some operation called plus. Like you can take a vector space in that case. Okay, for example, you take the vector space or some group also you can take it, where you can say like the operator plus is defined. Okay, so in that case, what I'm going to see is that f of x plus p or some binary operation you take it. Okay, so binary operation. Now I'm going to say f of x is defined for all values in this domain except some values. Okay, so except some points. Okay, in that case, that is first condition. Second condition is that if I take any p means I add it up p times. Okay, x plus p means I add that x plus etc. I'm just adding it, and then I get that. Okay, suppose I just add that f of x plus 1, f of x plus sorry, f of x plus etc. I'm just adding. Okay, means I'm just adding p times. Then what I should get is that if I get that, okay, if I get same thing, f of x. Okay, so f of x plus p means you are adding that x p times. Okay, so that is something similar. Okay, so what I'm going to say is that in this case we are going to say if f of x plus p is equal to f of x, okay, then we say that this is a periodic one. Okay, f of x plus p. So means if I just find some p such that f of x plus p equal to f of x, then I say that this is a periodic where this p should be greater than 0. Okay, so the two conditions are there. Function is periodic. Okay, function is periodic if f of x is defined for all x except at some point, possibly some points, there is some point p greater than 0 such that, okay, f of x plus p equal to f of x. Okay, for all x, this would be satisfied. Then we say this function is periodic. For example, you can take the sin x function. Okay, so for example, you can just take a simple example what we have in our real life. If you see a clock, the clock is actually doing the same thing. So if you just see after 12 hours, whatever my clock is having now, it will be after 12 hours, the same thing is going to come. Okay, so similar kind of things you can check for the days and months, etc. Okay, so for days you can see that after every 7 days, Monday is going to repeat, or after every 365 days, some year is going to repeat, something similar to that. Okay, so this is a periodic. So these kind of functions are occurring in many places in engineering, like engineering or geotechnical engineering, or even if you see the movement of the earth, etc. So every day, 24 hours, the sun is going to occur and it is going to show some lights to us, to the earth, and depending on the geophysical things, it will be varying. But this is the thing, like the sun is going to sunrise, sunset, etc. I can see. Okay. So now the same kind of logic will be applied in some of the engineering problems. For example, we have many times this function, step function. Okay, so it will just send some signal like this. Okay, step function, and again it will send something like this. Okay, so these are the signals it will send in. Similarly, it will send something like the functions like sine function, cos function. Okay, just periodic, just assume that this is kind of periodic function you are writing. Okay, so periodic one. So it should be having same trough and crest should be there. So this is the periodic function you might have seen. So these are the periodic function. So the remark here is that you need to see that the positive number p is called period of t. Okay, whatever I mentioned, the f of x plus p, the p is called the period of t. Okay, the smallest period is often called the fundamental period. Okay, the smallest period is called the fundamental period. And then we have the interval. Suppose it is, for example, if you take this one, okay, this interval. So if I take from here to here, okay, then it is going to repeat again. Okay, the same pattern is going to repeat. So this interval, suppose if I consider this one, let's say AB, this interval is called my window period. Okay, so the interval containing full period is called window. Okay, so some examples: sin x function, cos x function, tan x, cot x. These are all periodic function, and the periods are 2 pi, 4 pi, 6 pi, 2 and pi cancel. But the fundamental period is 2 pi. Okay, this 2 pi is also period, 4 pi is also period. For example, if I take this one, this is also period of the function. This is also a period of the function. Okay, means if I take from here to here also, this one get period of the function. But we are going to take only the fundamental periods. Fundamental period means only the smallest one which you are going to take. So in that case, 2 pi is the fundamental period for sin x, cos x, etc. And the windows you can say like 0 to 2 pi is one window, and 2 pi to 4 pi is another window, minus pi by 2 to pi by 2 is another window, etc. Similarly, if you take sin Lx and cos Lx, etc., then period is 2 pi by L is equal to 1. Same way, if you can check whether cos x, ln x, etc., x cube, are they periodic, etc. So some more questions now I have. Okay, so you can just check what is the period of sin power 4x and cos power 4x. What is the period of mod sin x into cos x, mod sin x plus mod cos x, and then some of the two sine function or trigonometric functions. Okay, so you can just answer this question. Have you come across any other periodic functions? Okay, anyone? Could you give an example? Have you come across any other periodic functions? So last two questions we answer. Have you come across any other periodic functions other than sin x cos x? Any answers? In school physics, school maths, or your BTech level course. Any other periodic functions have you seen? Am I audible?
Yes, sir.
Hello?
Yes, sir.
Yeah. Any other periodic functions have you seen?
SHM, simple harmonic motion, simple pendulum motion.
Harmonic function is something this is derived from trigonometry function, right? Harmonic function means it's going to have something like cos and sine, right?
Piecewise functions.
Yeah. Okay, just think of it. Now, next question: what will happen if you relax the condition p greater than 0? See, we have a condition p greater than 0 in that periodic function. Suppose p is greater than or equal to 0, what will happen?
Then the period will be 0, sir. When it will, when the interval will not be there at 0.
Means all the functions will be periodic. So if I just relax that condition p greater than or equal to 0, then all the function is going to become periodic because p of f of x is going to be f of x always, right? So f of x plus 0 means if p equal to 0, f of x plus 0 equal to 2 is going to come, but f of x plus 0 is again f of x. That means all functions are going to become like periodic. Okay, so the p greater than 0 is completely necessary. Otherwise, you will not get this f of x plus p equal to f of p. Means you cannot classify that. Okay, means you cannot classify, you cannot filter out some of the functions. Okay, all function is going to become like periodic. Okay, so this condition is important. One more question. So polynomials are periodic.
No, sir.
No, sir.
No, sir.
Okay, hyperbolic functions.
No, sir. Cos hx is not periodic.
Okay. Okay, so now what we are going to do, we are going to take a trigonometric system. Okay, what I have is I have something like 1 cos x, sin x. Okay, these two functions I'm going to take it. Okay, cos x, sin x, cos 2x, sin 2x, etc. I'm going to take. Okay, so this I call it as a trigonometric system. Okay, this I call it as trigonometric system. Okay, this system is called as trigonometric system. Okay, so based on this, I'm going to construct our thing. So all the elements are having 2 pi period. Okay, cos x is having 2 pi period, particular period, sin x is 2 pi, cos 2x 2 pi, sin 2x 2 pi, everything is having 2 pi period. 1 is also 2 pi period. If you take any constant function that is period with any period. Okay, 1 is a constant function, 1 is periodic with any period. Okay, therefore that is also we can consider it's a 2 pi period. Okay, so now. What we have is that suppose I have a sequence sin nx. Okay, this is a sequence n equal to 1 to infinity or n equal to 0 to infinity. Now, is this sequence convergent? If so, for what values of x? For what x does it converge?
0.
0. Okay. For x equal to 0, it converges. Any other x?
Sir, for any value of x.
2 and pi, sir.
Will it converge? Are you sure?
Pi.
How will it
sir.
converge? Convergence means what? It should come to one point, right? Sin nx will not converge all the time for all x. For example, you take sin 1, sin n. Okay. Assume x equal to 1. Sin n. Will it converge? Always? Will sin n converge always?
No, sir.
Converge to what? If it converges to what? Tell me. See, if it converges means it converge to one point, right? Where does it converge?
No, sir. We need to define one point. We need to value values of n.
One point. It is going to oscillate. Okay, it is keep on going to oscillate. Okay, it is not going to converge. Converge means it should converge to one single point. It is not going to converge at all. Okay, so x equal to 0, it is going to converge because sin nx is 0, so it is going to converge definitely. Okay. If x equal to pi, will it converge?
Yes, sir.
Okay. So if x equal to minus pi, 2 pi is also it is going to converge. Okay. So if x equal to pi, that is definitely going to converge. Even when you can take x equal to 2 pi, that is also going to converge. Same thing for cos nx. X equal to 0, it is going to be 1, so it is going to converge. Then any other points?
Pi by 2.
Any other points? Okay, think of it. Okay. Okay. Let's go to the next question. Okay. We know we have seen this definition already. Okay. Some an is a sequence. Then I have summation an. So summation an converges. Suppose. Okay. Suppose I have two conditions. Suppose an converges. An converges. Does it imply summation an converges? Suppose an is converging sequence. Can you guarantee summation an converges?
Yes, sir.
All right. For example, you can take this sequence. Okay, one by even you can take sequence 1. Okay, all an is going to be, I can take an equal to 1 for all n. This sequence is converging to the point 1. But if I take summation an, which is nothing but summation 1, which is nothing but infinite. Okay, infinite 1. So means I cannot put that infinite, it's going to converge to infinite 1. Because summation 1, if I add 1 n infinite times, it is going to give you infinite 1. Okay, so it is going to diverge. It is not going to converge. Similarly, you can take this one, 1 by n, which is converging to 0. Okay, but summation 1 by n does not converge. It is converging to, it is diverging sequence. Okay, it's a diverging one. It's not converging. Similarly, okay, next question. Suppose summation an converges. Means the series converges. Does it guarantee an converges? These are some of the basic BTech level questions. Does it converge or not converge? Any answer?
Yes, sir. It will converge.
It will converge. Okay, summation an converges means an is going to converge. Okay, there are theorems available. So you can take the sequence of partial sums from very control. Similarly, if you take sin nx, okay, now the question is we are going to ask whether summation sin nx converges. Okay, if so, for what values of x? You got to find x. Similarly, I can ask the question summation cos nx. Okay, summation cos nx, does it converge or not? Okay, summation cos nx, does it converge? If so, for what values of x? Same thing, I can just ask. Now I can take a sequence like summation an cos nx plus bn sin nx. Okay, or I can take summation. I can take all the combinations. Okay, an cos nx plus an sin nx. All these combinations, I'm going to ask this question whether it is going to converge or not, etc. If so, for what values of x it is going to do, etc., etc. I'm going to ask it. Okay, and also we are going to see what is the periods of that functions, etc. Okay, so if suppose this converges, we suppose this an cos nx plus bn sin nx converges. Okay, suppose I assume that this converges. What will be the period of the series for each x? So suppose this is converging. I assume that this is converging. An cos nx plus bn sin nx converges. Depending on the an, I can choose my weights. So these are the weight for that, or the coefficient for the series. Okay, I just called as weight as weight or the coefficient for that series. Okay, so what does suppose it converges? What will be the period of this function?
2 pi.
2 pi. Okay, it is going to be 2 pi. Okay, so suppose it converges. Okay, what we need to find is that whether we can find ans and bns. Okay, suppose this converges. Suppose the sequences are converging, then can we find ans and bns? That is another question we are going to ask. Okay, so these are the basic questions which we need to answer. Okay, and then we'll see. And we are going to define one more thing called orthogonality. Okay, So this is again going to be, we are going to deal that system once again. I'm going to deal with that trigonometric system only. I'm going to ask many questions and then we are going to formulate that Fourier series. So I thought that you might have seen in your school days physics or school days mathematics that if I have two vectors, okay, in the plane, suppose I have two vectors, okay, two vectors are there, let's say A and B. Then you can say two vectors are perpendicular or two vectors are orthogonal. Orthogonal means perpendicular, okay. If we find that dot product A dot B equal to 0, okay, so these two vectors I have. So if A dot B equal to 0, okay, then we say that this vector, these two vectors are perpendicular or two vectors are orthogonal, okay. So same thing you might have studied in your linear algebra course, okay. Suppose I have not only in these 2D vector, if I take a vector space, suppose I take any vector space, okay, or simply I can take R power n. So R power n I can treat as a vector space, okay. So in this case, once again I can define, what I can define is that I can just find what is my y transpose. Suppose I take two elements, okay, x comma y belongs to V, x comma y belongs to R power n, let's say, okay, V equal to R power. So y transpose x I got to find and x transpose y I got to find. If both are 0, then we say that x and y are orthogonal, okay. So we say that x and y are orthogonal. Similarly, in linear algebra course, you might have studied the vector inner product space. So instead of vector space, okay, instead of vector space in R power n, where I have defined this one, okay, I can just define this one, extra y transpose x and x transpose y, etc. Instead of that, if I just have a inner product space, suppose I have an inner product space, so in that case I can define inner product. Okay, inner product is nothing but a mapping, a bilinear mapping, okay, bilinear mapping between V cross V2 R satisfying set of properties like u comma v equal to v comma u and alpha u plus beta equal to etc. conditions are there, and u comma v greater than or equal to 0. So those some 3-4 conditions are there. So those conditions should be satisfied by the inner product space. So in that case, I can define this orthogonal. So u and v are said to be orthogonal. If you take u comma v, inner product with u comma v, that should be 0. Then also we say that it's a orthogonal. Okay, we say that it's a orthogonal. So this is a school physics to college physics or college mathematics. Now we go for the further one. So you might know like many of the continuous functions. So from the first class onwards, we are talking about some of the continuous functions. So the set of all continuous functions we call like function, that is also a vector space we can define. Okay, or even we can further define as an inner product space. So means C of A comma B, I'm collecting set of all continuous function from A comma B to R. Okay, set of all continuous function from A comma B to R. So in this case, once again, I can define my inner product. What I'm going to define my inner product is that since it is a continuous function, I can define their integration. Okay, that is going to become like suppose f and g are there. I can define their inner product. Okay, so f of x and g of x dx. I define the integral a to b f of gx dx. That should be 0. Okay, so this is 0. This is the inner product which I define. If this is 0, then we call it as f and g are orthogonal. Okay, now we are going to see whether our trigonometric system is going to be orthogonal or not. Okay, similarly, you can define orthonormal property. So in orthogonal property, suppose I take many functions, okay, f1, f2, f1, etc. I take a collection of functions, okay, collection of functions or a set of functions I am taking, and we say fj's are said to be orthogonal. So if I will say that this set, okay, I just take like f1, f2, etc., f1, etc. So I say this is orthogonal. When do I say orthogonal is that if I take fi comma fi, the inner product with fi, the inner product means inner product of fi comma fj is going to be 0. If it is 0, then I say that means fi of x into gi of x dx be equal to 0. Then I say that this is a orthogonal. Okay, this complete all functions of fi's are said to be orthogonal. On the other hand, suppose you have orthonormal. In that case, what I need to do is that I got to check what is the inner product with respect to itself. Okay, fi dot fi. I mean here. Orthonormal means if I take a dot b, okay, if I take a dot a, or here I take y x transpose y instead of that x transpose x, that is going to become like 1, okay, for the complete set. So this is the basic idea behind that. Many of the problems in linear algebra which you might have seen, like finding the orthonormal basis, etc. Okay, so the Schauder basis, orthonormal basis, these two things we might have here in the linear algebra courses. So something similar to that. Here what I have orthonormal. So this set I say it is orthonormal. Or set of functions I call it as orthonormal. Fi comma f should be 0. If I take the inner product with itself, okay, means fi comma f I, okay, instead of fi comma f j. If you take inner product fi comma f I or fi comma f j, sorry, fj comma fj, okay, fi comma fi, then it should be 1. Okay, then I say that this is orthonormal. Okay, now we are going to see whether our trigonometric system is orthogonal or orthonormal. Okay, this is the basic idea which is going to help us for developing the Fourier series further. So let us see that. So let us see what is the idea behind that. Okay, let us find that. So let us take this series. Okay, so cos x, sin x, cos 2x, sin 2x, etc. We are going to prove that this is going to be an orthogonal set. Okay, this is going to be orthogonal set. And further we can define one more set that is going to be like orthonormal set also we can define. Let's see that. Okay, so let's prove this theorem. So this theorem is saying that suppose I have sin nx, sin mx. I can take this one. Okay, so you take this one f1, f2, f3, etc. Okay, so in general I can take any two functions over there. I'm going to see whether sin nx and sin mx, what is the value of this. Okay, similarly I'm going to find, so combination, all combinations I can take. Okay, n not equal to m. For example, if I take n not equal to m, sin nx, sin mx I can take, sin nx, cos mx I can take it, cos nx, sin mx I can take it. Okay, and then I can take cos mx, sin mx I can take it. Okay, now question is, what is their properties going to come? Okay, so that we are going to see. So the theorem is claiming is that if I take this from minus pi to pi, okay, minus pi to pi, this interval only. Okay, so this theorem is claiming is that these are all 0. Okay, these are all 0. So n not equal to m, so this is going to be 0. In particular, for this some of this, even n equal to m also it is going to be. Okay, that also we are going to see. Okay, cos nx, and you can even take cos nx, sin nx also you can take it. That is also going to become 0. So these are all going to be. This is almost same. Okay, cos nx and sin nx, this is same. In particular, so one more I can write. So cos nx, sin nx also. This is also going to become 0. Okay, so here cos nx, sin nx, these two are almost same. Okay, only n and m are different. So I can take this cos nx and sin nx also. That is also going to become 0. That's once again from the simple school mathematics. Okay, so we know that for n not equal to m, what I have is that I have this property minus 1 to minus pi to pi. Okay, cos n plus or minus m of x equal to minus sin n plus or minus m. Okay, into x divided by n plus or minus m. Okay, so I take this n not equal to m because once I define here n minus m term will come, so that should become like infinite, means it is not defined. That's the reason I am taking n not equal to m always. Okay, so in this case what I have, but if I am taking without minus plus, then n equal to m is also not a problem for me. Okay, that is going to be the same reason. So this is minus pi to pi. Okay, sin at minus pi and plus pi is going to become 0. Okay, n and m are integers here. So n pi and m pi, sin n pi and sin m pi, they are going to become 0. Therefore, this is going to become 0. Okay. So similarly, if I take minus pi to pi, okay, sin of n plus m into x, sin is an odd function. Okay, if it is an odd function, minus pi to pi, then that is going to become like 0. Okay, sin is an odd function. Therefore, irrespective of n equal to m or n not equal to m, it is going to give you the value as 0. Okay, so that is that. Now we have this trigonometric identity which you might have seen in your 10th standard or 11th standard. So sin of a plus b, a plus or minus b equal to sin a cos b plus cos plus or minus a, sorry, plus or minus cos a cos b. Similarly, cos a plus or minus b equals c. So that's what we are going to use it here. So I can write sin nx, sin mx. Okay, sin nx and sin mx I can write it as half into. Okay, this one I can write it as half into. Okay, sin nx into sin mx I can write it as half into integral. So from the previous two identity, you can just get that cos n minus m into x minus 1 by 2 into sin, sorry, again cos n plus mx dx. Okay, so this is the one which we have. but I know already minus pi to pi, so this is minus pi to pi, okay, minus pi to pi. This is already 0, which we got to. Therefore, this is 0, this is 0, so sum is going to be 0. Similarly, I can define where is my cos? Okay, I didn't define cos. Okay, this is two things same here. Cos mx, I define one more thing. Where do we change? Okay, here I will change. Okay. Cos mx system. Okay, so in this case, what I can define, I can do the same thing. 1 by 2, this is going to become like minus pi to pi cos n minus mx plus 1 by 2 cos minus pi to pi cos n plus mx is going to come. So this is the. So this is once again first is going to be 0 because of this property. Second is going to become 0 because of the this one. Again now, if I take sin mx and cos mx, okay, using that identity again, what you can prove is that it is going to be 1 by 2 sin n plus mx. Okay, this is going to become like 1 by 2 into sin integral sin n plus m into x plus once again 1 by 2 minus pi to pi sin n minus m x dx is going to come. But again, this is odd function, so that is going to become 0. Therefore, it is going to be true. And here it is irrespective of n and m. Okay, n is equal to m or n not equal to m, doesn't matter, it is going to be true. Okay. Now, if we come for the other one, okay, the last one. Now, the other one, what I call is that for cos nx and cos mx are again the same thing is going to come. Cos nx and sin x is going to become the same thing because simply you can say one thing. It's an odd function, it's an even function. If you multiply odd function with an even function, that is going to be an odd function, therefore it is going to become 0. Okay, that is also trivial function. Now we have n equal to m and n both are this is going to become like sin square mx, so it is going to become like 0. Okay, cos 0 is 1, so dx is going to become, this is going to become like n plus mx. Okay, so that is going to become like cos 2nx is going to come. Now for cos 2nx it is 0, okay, because n plus m is there, that is going to become 0. Only this is going to survive. Cos x is going this is going to be dx is going to be there. So dx is nothing but x. So pi to pi is going to come 2 pi. So pi 2 pi and 2 gets cancelled. So pi is going to be the answer. Same way you can apply here cos square nx. So this is going to become like dx is going to come. This is going to become 0 because of this property. So you are going to get once again pi is going to come. Now if you go for sin square nx, that's again going to give you the same kind of thing. So sin square nx is going to become like, this is going to become like sin 2nx, that is odd function, so going to become 0. Sin 0, so n equal to m, so sin 0, so that is going to become 0. That will be 0. Now if you go for cos square nx, okay, cos square nx means suppose I put n and m are, okay, so n and m are equal to 0. Okay, n equal to m equal to 0. In that case, what I'm going to have, so this is going to become a cos square, so 1 into 1 dx is going to come. So integral minus pi to pi is going to give you the answer as 2. So therefore, what you have proved is that this trigonometric system is orthogonal system. Okay, if you take any of these one, what you are going to get is that you are going to get all these things are going to form a the trigonometric system is going to form a orthogonal system. Okay. Now, again, here what you can do is that I can define something like I need to make it as orthonormality. For orthonormality, what I require is that I require that should satisfy. If I take the inner product between them, that should satisfy that one should come. Okay, it should give the answer as 1. But here, once I do the computation, if I take the inner product itself, it is giving pi or 2 pi is going to come. So in that case, I need to divide that. If I divide that, then I may get the orthonormality is going to come. So for dx, it is going to 2 pi, okay, minus pi to pi dx, which is nothing but the first term, 1 into dx, you can write it. So that is going to give you the answer as 2 pi. Okay, so therefore I just define that as 1 by square root of 2 pi. Then that is going to give you the, if you integrate, then that is going to give you the answer as the answer is going to become like 2 pi is going to come. Means if I take cos x, okay, so I just take 1 by root 2 pi into 1 by root pi, etc. So we take the inner product between them, that is going to be the orthonormality. Similarly, you can take for the sine also 1 by root pi, because 1 by root pi, if you multiply 2 terms, okay, then that is going to become like 1 by pi is going to come. Then you are going to get sine 2x is going to come. Okay. Similarly, we are going to exploit this idea. Okay, we are going to exploit this trigonometric system and its orthogonality property and the orthogonality property to obtain some interesting series. Okay, these series are very nice and they are entirely many nice properties whatever we have defined here. Okay, because if I take inner product with itself, it is going to give you some answer. If I am taking inner product with the other term, I am going to get the answer as 0. Okay, so this is having a nice property, and we are going to use that as some of the filtering. So this is the main motive for main interesting property for many of the engineering application. Suppose you want to signal out or you want to filter out some of the signals in electrical engineering or some of the geotechnical signals, etc. What you are going to do is that you are going to use this kind of series so that it is going to filter out some of the values from the signal which you are receiving. Okay, so that's a basic idea here. We are going to use that and exploit that, and we are going to. Now let us revisit our big question which we asked. Suppose a n cos n x plus b n sin n x converges. What will be the periods of this series? Already someone has answered. The period is going to be 2 pi. Okay, suppose it converges, the period is going to be 2 pi. So I said it is convergent. So if it is convergent, it is going to converge to some values, right? So suppose I have summation a n cos n x plus b n sin n x is there. This is going to be convergent. So if it converges, it should converge to some point, right? For each x, it is going to. So if I take any x, for this it is going to converge. Therefore, what I am going to take for each given x, I am going to assign. Okay, I am going to define some function f. Okay, f of x. So for each x, it is going to converge. So f of x equal to summation a n cos n x b n sin n x. I am going to. So the x is a function such that this is going to be satisfied. So if this is a period of 2 pi, then f is also having. F is also period 2 pi. Okay, f is also period 2 pi. This is having period 2 pi. So we are going to use this and exploit this to construct the Fourier series. So that's what we are going to do in the next 20 minutes or 15 minutes. Okay. Suppose the series converges. Okay. Then we can find the coefficient of f a n's and b n's by exploiting the orthogonality property of the trigonometric system. So what we are going to do is that I said already that this is going to converge. Okay, this is going to converge. So we have all these properties. Suppose this is converging, etc., and we have this continuity, etc., is going to be there. Okay, suppose if it's a continuous function, or even you can take piecewise continuous function also. That we are going to take it later. So if you say like this is going to have a continuous function, it is going to be there because cos is a continuous function and sin x is a continuous function. Okay, so summation is going to be continuous if the sum is going to converge. There are many more analysis is available here. Okay, so you need to take many of the things. It should have some uniform convergence, etc. should come. Then only this is going to be satisfied. Cos is continuous, sin is continuous. Therefore, sum is going to be continuous. You have infinite series. Therefore, you need to know more about that, like uniform convergence, etc. will come to the picture, and then you have to see that. So in that case, you can say that this is going to give like f of x is going to give you the continuous f of x is going to be like continuous. This is going to converge. Okay, suppose summation a cos x and sin x is going to converge. Now what I can do, since it is continuous, this fx is continuous, I can just integrate. Okay, I'm just going to put the integration. I'm multiplying sin mx. I'm going to multiply. Okay, minus pi to pi sin mx. So this is going to become like summation. Again, put n equal to infinity or n equal to 0 to infinity. Okay, a n cos mx. Okay, integral into I'm multiplying sin mx. Okay, plus summation. So again, summation is here. Okay, bn integral sin nx sin mx into dx is there. Okay, the integral is from minus pi to pi. Okay, so in this case, you can see that when this is going to exist. Okay, so this summation is n equal to 0 to infinity. I can put it. Okay, so I got to see when this is going to be true or when it is not going to be true. So if I multiply by sin mx, what it is going to become? Cos nx, if n not equal to m, okay, if n and m are different, then this is going to become 0. Even if n equal to m also, okay, this is going to become 0 because sin nx and cos nx, sin is a odd function, cos is even function, that is going to become 0. Whereas here, if I come over here, then what I am going to get is that when n not equal to m, this is going to become 0. When n equal to m, what I have as per the orthogonality property or orthonormality property, we have that this is going to become like b n into pi or b m into pi is going to be. Okay. when n equal to m. Okay, when n equal to m, I'm going to get bm into pi is going to come. Therefore, what I can define bm or bn. Okay, because m and n are equal, so I define it as bn. So bn is going to be 1 by pi. Okay, bm into pi is that. This is going to be bm into pi. So I define bn equal to 1 by pi minus pi to pi f of x into sine nx. Because n and m are equal, I can replace that. Okay, so this I found. Now same way what I can do. So I found bn. So bn is going to be 1 by pi minus pi to pi f of x into sine nx dx system. Now I have to replace the same thing. Okay, instead of sine, I am going to cos here. If I put cos here, again this is going to be cos. Okay, this is going to be cos. Okay, so this is going to become 0 because irrespective of whether n is n equal to m or n equal not equal to m, sine is even, sine is r, cos is even. So multiplication is going to become r. So r times it is going to become 0. So then only this is going to be there when n not equal to when n not equal to m. What I have that going to become like 0. Okay, when n not equal to m, it is going to become 0. When n equal to m, okay, there are two cases we need to discuss now. First case is a naught. Okay, if I take n equal to 0, what I am going to have, a naught is going to become like cos 0, cos n equal to m equal to 0. Okay, first case n equal to m equal to 0. Okay, so in that case, what I am going to have, I am going to have cos 0 is 0, cos going to become 0. So in that case, I'm going to get it like this is going to become minus pi to pi dx is going to come. So a naught into 2 pi is going to come. Okay, if n equal to m equal to 0, then I'm going to get a naught equal to 2 pi is going to come. So that means a naught into 2 pi is going to be f of x into cos 0. Okay, m is 0, therefore this is 0. So this is going to become like 0 dx is going to come. Therefore, what I have, a naught equal to 1 by 2 pi minus pi to pi f of x dx is going to come. Okay. Suppose n equal to m. Okay, n is not n equal to m, but they are not equal to 0. Okay, not equal to 0. In that case, what I have an is going to be surviving, remaining all going to become 0. Okay, an everything is going to become 0. Only an is going to survive. Okay, an term is going to survive. In that case, cos square nx is going to come, but in minus pi to pi cos square nx, we have already proved that is pi. Okay, therefore, what I am going to have, I am going to have an equal to 1 by pi minus pi to pi f of x into n and m are equal. Therefore, I am just replacing this cos of x. So that means what I am going to have is that I am going to have, if I have this f of x is converges, means this trigonometric system or this trigonometric series, whatever I have written here, if it is converging and converges to a function f of x, okay, and we have many more conditions like continuous, etc. is going to play the role. Okay, we have conditions are becoming in the picture. Now what we have is that we are having, suppose this is happening, then we can find this a and b. Means our question was how to find this a and b. Suppose this fx is converging. So this is going to be your sequence. Okay, the series is going to be summation n equal to 1 to infinity. So a naught is going to be separate. Okay, summation n equal to 1 to infinity an cos nx. Okay, b naught is already 0 because that is not going to survive. Okay, and then we have something like bn sin nx. Okay, so this is called, if I write this as f of x, this is called the Fourier series. Okay, and where ans and bns, a naught, ans are given. Okay, so this is called the Fourier series definition. Suppose that f is a given function with period 2 pi and such that it can be represented by f of x equal to summation an cos nx plus bn sin nx. Okay, that is above series converges and its sum is f of x. Then for r n equal to 1 to infinity, you can define this. Okay, you can define this ans, bns, and a naught. That is going to represent the Fourier series. Okay, next one. So this is an example. I'm not going to solve it. I just show it in the slide itself. So f of x equal to minus k if minus pi less than x less than 0. K if it is 0 to 0 less than x less than pi. Okay, I don't care what is that at one point. So at one point means at x equal to 0, I don't define anything, but it doesn't matter for me. Okay, because at one point if you are not defining, the integral is not going to affect much. Okay, you can just split that integral. So what is it going to become? Okay, so this is an even, this is an odd function. F is an odd function. Okay, so F is an odd function, then minus pi to pi f of x dx, that is going to become 0. Means a naught is going to become 0 because F is an odd function. Now again an, that is going to become like F is an odd function, cos is an even function. If you multiply an odd function with an even function, that is going to give you an odd function. Therefore, that is also odd, and you are going to get the answer as 0. So Bn is going to survive because F is an odd function and sin is an odd function. Odd into odd is going to give you even. So that is, I can write it as, if it is an even function, you can write integral minus pi to pi as 0 to pi, you can write it. 2 times 0 to 5 you can write. So 2 I am taking it out, and f of x equal to k, so I kept it k outside. Okay, and sin nx we got to integrate. If I integrate sin nx and 0 to pi, I am going to get the answer as sin n pi by pi is sin nx by nx, n is going to come, so n I take it out and apply the limit. So you are going to get that 1 minus cos n. So this I can write as 1 minus 1 power n, because cos n pi is minus 1 power n. So I can write this as 1 minus of 1 power n by n into sin nx. So this is going to survive only if you have even terms. Okay, only when n is even, this is going to become 0. Okay, when n is odd, 1 plus 1 is going to come, that is going to become like 2. So that 2 I am taking it out. Therefore, this is going to become like 4k pi pi. Summation n equal to 1 to infinity 1 by 2n minus 1 sin 2n minus 1 is going to come. Means only odd term is going to survive. So this is another observation. You can see that if you just put f of pi by 2, then you can write that k equal to 4k pi by summation n equal to 1 to infinity 2n minus 1. And you see that some interesting property here, because you know, one of the main challenging tasks, or since the history of mathematics, since Archimedes or even Pythagoras, many people have tried to find what is the value of pi. Okay, they are trying to find what is the value of pi exactly, that we cannot find still now because irrational, we can't express that. But at least we can write that pi as a series of some terms. Okay, for example, you see that pi by 4 equal to summation n equal to 1 to infinity minus 1 power n plus 1 by 2n minus 1. This is going to represent a series representation for pi. Okay, pi by 4. So you can just, that from this you can calculate your pi value also. So some of the computers, what they do is that they use something similar to that to calculate what is the value of pi. Even there is other series like tan x series also, or tan inverse series also, you can use it to find the values. So this is the way computers are calculating the values of pi many times. Okay, using the series representation, it will find that. Okay, okay. So this is another important, interesting property which you obtain from Fourier series. Okay, okay. So which we have seen. So what is the condition we have for the representation by Fourier series is that, so suppose f is periodic period 2 pi and it is piecewise continuous in the interval. Okay, so it is not necessary that it should be continuous, it can be piecewise continuous in the interval. And suppose we have f have left and right derivative. Means on the left side you have a derivative, and right side also you have a right hand derivative is there at each point of that interval. Then suppose this series converges, this Fourier series, whatever I have written, is converges, and its sum is f of x, except at some points x naught where the f is discontinuous. Because it is piecewise continuous means there will be some discontinuity there. Then this is going to say the sum of the series. What is the sum of the series at that discontinuous place? Okay, that is going to be, you can take the, suppose this is discontinuous at x naught, what you can do is that you take the left limit, okay, and right limit for that, and then calculate the average of that. That is going to be the limit of that function at x naught. Means you can, suppose you, this is very interesting property for engineering problems, because suppose you lost some signal, you are receiving some signal from some satellite or some kind of communications which you are receiving, either geotechnology or something, or even sending some signals to the earth and etc. you are going to do. What is happening is that, suppose you have you are receiving some signals continuously, at some point it got breakdown. Okay, then in that case, suppose you want to find that missing place, some places the value is going to be missed out. If you see some of the geotechnical problems or engineering problems, some of the value is going to be missed out. So in that case, how do you fill that value? So you can fill that value in such a way that, since you are represented using the Fourier series and this is going to exist, that you can obtain the right hand limit and left hand limit and take the average of that. That is going to give you the limit of going to give you the values of that f at x naught. Okay, the limits of f at x naught also can be. the proof of this theorem is an advanced topic. You can just refer some of the textbook like trigonometric series. Okay, I will take another 2 minutes to explain this Fourier series period 2L. Suppose so far we have defined period 2 pi. Instead of that, suppose I have 2L. Okay, instead of period 2 pi, I have 2L. So in that case, what I can define is that I can define that okay, yeah, period 2L. So in that case, what I can do is that suppose the period is p equal to 2L, then we can use the transformation. Okay, you can use the transformation x equal to p by 2 pi into nu. Okay, so now suppose p equal to 2L. Okay, p equal to 2L. Then if I substitute 2L here, this is going to become like nu is going to become like, okay, let's see what is nu. Nu is going to become like 2 pi by p into x is going to come. Okay, so if I substitute p value over there, what I'm going to have? I'm going to have 2L 2 will get cancelled. I'm going to have p equal to 2L. Therefore, this is going to become like pi by L into x is going to come. Okay, so x is, if x is ranging from x is belongs to minus L comma L. Okay, then where it is going to become, if I put x equal to minus L, okay, then nu is going to become like, if I put x equal to minus L, nu is going to become like minus pi. If I put x equal to pi, nu is going to become like pi. Means if x is belongs to minus L to L, then nu is going to become like minus pi to pi. Means I did the transformation from x to nu transformation. Okay, where nu is defined from minus pi to pi, and that transformation is going to give me the transformed function f is going to give me the periodic function with period 2 pi. Therefore, I can again write that expression. Okay, using the Fourier series, I can write that. So wherever I have x, where I can replace that with so for that I can write it. So means I have a new function. Let's say g is that. So g is going to be a new one. Okay, which is a function of nu. That is a function, periodic function with period 2 pi, the interval minus pi to pi. So in that case, I can represent the Fourier series. Okay, wherever I have x, replace with nu. Okay, wherever I have x, replace with nu. Okay, let me say this is g nu. Okay, for example, this second is g nu. So this is going to be nu. This is going to be nu. Okay, wherever I have nu, I can just put that one. Nu or v, whatever you call it. Okay, nu. I'm going to replace. Okay, wherever I have x, I replace with nu. So now, what is nu? Nu is nothing but pi by L into x. Okay, nu is nothing but pi by L into x. So that means, okay, that means I can write that x is equal to L pi by v also I can write. Okay, so that means here what I'm going to replace is that I'm going to replace that wherever that x was there. Okay, wherever x was there, there I'm going to replace it with L pi by v. I'm going to replace. Okay, so I'm going to replace wherever that value was there. I'm going to replace that with L pi by v. Okay, so you can write that, okay, n pi by, so wherever I have nu, that you replace by n pi by lx. Okay, that is going to become like, you can just replace that with n nv is there. So wherever nv is there, you replace with this one. So this is going to become like pi n pi by n into x is going to come. I'm going to transform it to once again to f of x. Okay, so n pi by L into x is going to come. Similarly, you can replace it over here. Okay, so if you replace that, once again you are going to get the same thing. So this is a dummy variable, so I can just put that like x is going to come. So this is going to become like, once again, sine n pi by Lx is going to. Okay, same thing you can do. Same thing you will do. Okay, so that is going to give you the answer for period 2L. So the same problem you can do that minus k to k, where minus 2 to 2 is there. Instead of minus pi to pi, you are going minus 2 to 2. So same thing is going to come. Okay, same logic is going to come. an is going to be 0, bn is going to be surviving only if n equal to m. So that is going to be there. Again, you can write that fx. So instead of 2n minus 1 into pi x, this is going to become like 2n minus 1 pi by 2x is going to come. There is a small mistake there. That should be n pi by 2 is there. Is cos n pi by 2. So that's what you are going to get. You are going to get this one. So last one, suppose your function is periodic. Okay, so suppose your function is periodic, which has even function, then you can get a cosine series, because if f is even, what is going to come? Okay, if f is even, let's take this one. Okay, suppose f is even function, then we can check here. F is an even function, then what is it going to come? It's an even function, this is an odd function, so even into odd is going to be odd, therefore this is going to vanish. That means b's are 0, bn's are 0, so this is going to vanish. We are going to survive with only cos. Okay, so therefore this is called Fourier cosine function. Now suppose f is an odd function, then f is an odd function means this is going to become 0. It's an odd function, this is an even function, so odd into even is going to become like odd, so this is going to become 0. So an's are going to become 0, so therefore this is not going to survive, this is not going to survive. Only bn is going to survive, because this is an even function, this is an odd function, so you can get that value. Okay, so that is called Fourier sine series. Okay, with this I will stop, and we have some more exercise problems. Okay, in tomorrow's class we will see the in the Friday's class we will see the Fourier integral and Strum Liouville problem, and then we will go ahead with PDE problems also. Okay, so the take-home message is that we have a trigonometric function. Okay, trigonometric system is that. From that trigonometric system, you constructed a series. Okay, you have asked many questions, and you constructed a series, and you assume that f is converges. If it converges, then we have a representation. In other words, if f is a function given to you in a period 2 by f is a periodic function given to you, then what you can construct is that you can write that as a Fourier series. You might have seen some series like Taylor series or like Maclaurin series earlier. Something similar to that, what we are doing is that we are going to write that as Fourier series. This Fourier series is going to give you in terms of sine and cos.